In the video of introduction to moles and molar mass, I explained how many atoms were in a mole of a substance. So now we're going to look at how to use that number. Our first question here is 3.87 moles of a mystery substance has how many atoms? So we don't know what the substance is, but that doesn't matter because 1 mole of any substance, as we said before, equals 6.022 times 10 to the 23rd atoms. Avogadro's number. So this conversion is pretty easy. We have 3.87 moles. We need to find out how many atoms. So we're going to multiply by atoms because that's what we want. So it's going to go on top. And we're going to divide by 1 mole. Our moles will cancel out. And we will get 2.3305 times 10 to the 24th. Atoms of our mystery substance. Now our question, we've got 3 significant figures here. We've got 4 in the number that we're using for Avogadro's number. So we need to round to 3 significant figures here. When you're in scientific notation, all of the numbers in your coefficient are significant. So we're going to look at the first 3, 2.33. That 0 is going to keep that 3 a 3 times 10 to the 24th atoms. And that would be the correct answer to this question. Looking at the next question, I'm asking, we have 6.022 times 10 to the 23rd atoms of iron. How many moles of iron do we have? So this time, made this one pretty simple. 6.022 times 10 to the 23rd atoms of iron. We want moles this time, so we're going to multiply by 1 mole. Every 1 mole has 6.022 times 10 to the 23rd atoms. So our atoms will cancel out and we'll end up with moles. Now I use the same number here, so we're going to find that we have 1 mole of iron. However, both of our numbers here, 6.022 and 6.022, have 4 significant figures. So our correct answer would actually be 1, my pencil's not working, 1.000, so we get all 4 of our significant figures. Mole or moles of iron. Okay. Now we're going to use that information. We're going to go a step further. But first, we're going to trade some bananas for some pineapples through the mango. The mango is going to represent our mole in the future because, as I like to say it, moles are always in the middle. You can't get from atoms to grams or grams to atoms without going through moles. In this case, we can't get from bananas to pineapples without going through mangoes. So I have 6 bunches of bananas. And I want pineapples. But the guy who's willing to trade will only accept mangoes. How many pineapples can I get? So the first thing I need to do is I need to trade my 6 bananas for mangoes. So I don't know what's going on with my pencil. 6 bananas times, I want mangoes, so 4 mangoes for every 1 banana. This is bunches of bananas. And that's our conversion factor there. Will tell me how many bananas I have. So I have, or how many mangoes I have. So I can get 24 mangoes because our bananas will cancel out. But we don't want to stop there. So we need to take our mangoes and figure out how many pineapples we can get. So this time we're going to multiply by 1 pineapple for every 3 mangoes. Our mangoes cancel out. 24 divided by 3 means that we can get 8 pineapples for our original 6 bunches of bananas. Everything had one significant figure there, so 8 is the answer. Now, I gave that example to show that we couldn't go straight from bananas to pineapples. We had to go through the mangoes. And when we had to go through the mangoes, that got us to like term, or something that was equal that we could compare to both. So now I'm going to do a question on going from atoms to grams. So like I said before, moles are always in the middle. That's important. Your moles, if you're doing a multi-step conversion in this case, the moles is going to be in the middle. Later on, we're going to add another extra possible step with moles, but they will still be in the middle. So moles are always in the middle. We have 1.897 times 10 to the 23rd atoms of iodine. And we want to know how many grams of iodine we have. The first thing we have to do is figure out how many moles of iodine. So we're going to take this, we're going to use Avogadro's number. We're going to say that 1 mole, because that's what we want, so it goes on top, over 6.022 times 10 to the 23rd atoms. Now our atoms will cancel out, and we will see that we have moles now. And then after that, what we need to do is multiply by the molar mass of iodine. So let's find that number real quick. Iodine, 126.904. So 126.904, we got 2 of them. So, what? And add on my calculator. $253.808. That's grams for every 1 mole. So we want to get rid of moles now. So moles is going to go on the bottom. And our 253.808 grams will go on top. And that will give us our answer. So now all we have to do is plug in all these numbers into our calculator, and we should be able to get the correct answer. So 1.897 10 to the 23rd divided by 6.022 10 to the 23rd As you can see, it's divided by because the 6.022 is below the line. And then we're going to multiply by 253.808 times 253.808 equals 79.95 grams of iodine. Let's say 79.952. So we get 79.952 grams. Now we look at our problem. We've got 4 significant figures. We've got 4 significant figures in here. We had to look at this number, which had 6. So we need to round this to 4. So our final answer would be 79.95 grams of I2. Oh, I didn't set up another problem, so let's set one up real quick. Now we're going to go from grams to atoms, just so we can know that process as well. So let's say that we have, we'll use water. We use water a lot. Water seems to play a vital role in our daily lives. Let's say we have 24.3 grams of H2O. So what we need to do is find our molar mass of water. So H 1.00794, I believe. Let me look. Oh, 784, way off. Oxygen, 15.9994. Multiply this by 2. And I know we've done this calculation before, but we'll do it again. 1.00784 times 2 plus 15.9994. Is this 18.01508? Now we'll just go ahead and use that whole number. We're not going to round anything off until the end. So we have 24.3 grams H2O. We know that this is how many grams there are for every 1 mole. We need to go to moles. Moles are always in the middle. So 1 mole over 18.01508 grams. Our grams cancel out. And then now that we have moles, we can go to atoms. We know that 6.022 times 10 to the 23rd atoms are in every 1 mole of anything, which I guess in this case it's molecules, not atoms. Let's fix that. And then all we have to do is punch it into the calculator. So we're going to take 24.3. 24.3, we're going to divide by the molar mass of water, which we still had in our calculator there. And then after that, we're going to multiply by Avogadro's number here. So 24.3 goes to below the line. So we divide by 18. We multiply by 6 by the next one. So multiplying by Avogadro's number. And we get 8.1228 molecules of H2O. Go back to our problem. We had 24.3, 3 significant figures. Avogadro's number in this class will always have 4. Our molar mass all had greater than 3, so we need to round this. Oh, I forgot the times 10 to the whatever. Times 10 to the 23rd. Molecules of H2O, so we're going to round this to 3 significant figures because of the 3 significant figures in this number. So 8.12 times 10 to the 23rd molecules H2O. And that is a few example problems of going from atoms to